Hi everyone, we are the students of GM University and today we are here to present our assignment on the course operating system. So I am Abhiram. I will walk you through the parallel sorting with child processes, a program that efficiently sorts large data sets by utilizing multiple processes running in parallel. This assignment showcases system level programming, emphasizes process creation, inter-process communication and efficient management of resources across Windows and Unix system. The main goal of this program is to sort a massive data set of 10 million integers using parallelism to achieve faster results compared to a single thread sorting process. So in here we generate a data set and split it. So we generate 10 million random integers and split them into 10 subarrays, 1 million integers each. Parallel sorting with child processes. We create 10 child processes which are responsible for sorting the subarray. This division leverages multi-core process, enabling simultaneous sorting of all arrays. Inter-process communication using shared memory. We use shared memory for efficient data exchange between parent and child process. Once all the sorting is done by the child process, we merge it into a single array using optimized merging algorithm. This process not only highlights the power of parallel computing but also demonstrates system level operations like synchronization and memory management. So the code is divided into two main components, parent.c and child.c. The parent process oversees the entire operation and it generates a data set and split it into 10 subarrays. So using create process, it creates 10 child processes which are responsible for sorting each subarray. So we pass the subarray as an indices to the child process via command line arguments, and we also set up a shared memory setup through which the child and parent process can communicate with each other. So once it is done, the child process is responsible for sorting and sorting each its assigned subarray through the shared memory access. It connects, and once the sorting is done, it pushes the sorted array to the parent via shared memory. So to summarize it, parent.c generates and splits the dataset, creates child process and merges the sorted array, whereas the child process.c sorts the subarray and communicates result back to the shared memory. Thank you. The further code part of the assignment will be explained by my friend Prajwal.
Yes, thank you, Aviram. My name is Prajwal. Today I'll be explaining you about parallel sorting programs consisting of two key parts, parent.c and a child process.c. This system is designed to sort a large dataset efficiently using a multiple child processes and share memory for inter-process communications. I'll explain how these two programs work together and divide the sorting task and perform the work in parallel and merge the result. The parent.c file. It is the main program responsible for coordinating the entire sorting operations. It creates the large dataset, divides it into a small subarrays, creates a child process, waits for them to complete, and then merges the sorted subarrays into a single sorted array. Then let's start by looking how we set up our program in the parent.c file. The program includes number of libraries like windows.h, which specifies the functions like process creations and shared memory handling. Stdio.h and time.h are for general operations like printing and output, handling random numbers, and timing the operations. String.h is used for string manipulations like forming the path to the child process.exe. And we also have defined some important constants like array size, num process, sub array size, which is used to calculate and which is calculated by dividing the array size by num process. So each child will handle an equal proportion of the data sets. Next, we'll retrieve the full path of the current executable get module file name. This is crucial because we need to know where the parent program is located to later construct the path for the child process.exe. Then we use this path to create a full path for the child process.exe file. This is the executable responsible for sorting the subarrays. After that, we initialize a unique name for the share memory by combining a sorting memory with the current processing ID. ensuring that the different runs of the program won't collide in shared memory namespace. We create the shared memory by using a create file mapping. This memory is large enough to hold an entire data sets of 10 million integers. Once the memory is created, we map into the parent's address, spacing using a map view of the file. So the program then proceeds to generate 10 million random integers using a rand function. These random numbers are stored in the shared memory that was created earlier. This shared memory will allow the child processes to access and modify the data. Now the parents need to swap 10 child process. It does this using by create process function in a loop. For each process, we prepare a command line with the start index, subarray size, and map name. The parent uses the create process function to swap each child. If the process creation fails, the program prints an error and exits. Once all the child processes have been created, the parent waits for them to finish. This is done by using wait for signal object to block until each child process completes its tasks. After each child finishes, the parent closes the handles and child process and threads to free resources. Now that all the child processes have finished their sorting, the parents needs to merge the results. The parent uses a temporary array called temp to merge the sorted subarrays. We use multiple pointer approach to find the smallest element across the subarrays and place it into the final sorted array. This is similar to the merge step in the merge sort algorithm. After merging is complete, the parent writes the final sorted array to file called sorted array.txt. So stay in a call. To measure the performance of our parallel sorting approach, the parent records the start and end time using clock. This allows us to see how long the sorting process takes and compares it to a single process sorting methods. Finally, the parent unmaps the shared memory and closes the handle to clean up it after itself, ensuring that all the resources are released before program terminates. Now let's come to the child process.c. So as shown here, this is the child process.c. This is much simpler as compared to parents.c. Its main responsibility is to sort the portion of the array that is assigned to it by the parent process. It receives a smart index, a start index, subarray size, and a shared memory name as command line arguments. The child first checks the command line arguments to ensure they are correctly passed. It accepts three arguments: a start index, a array size, and a mapping name. By using open file map, the child process accesses a shared memory created by the parent. If this operation fails, the child prints an error message and terminates. Once the share memory object is successfully opened, the child maps opens the share memory into its own address space using map view of file. This allows the child to access the data directly. The child then sorts its assigned subarrays using a qsort function. It passes the subarrays to the starting at pbuf and the start index, thus array size to qsort. The compare function is used to sort the integers in ascending order. The sorting is done in a place, meaning that the child modifies the shared memory directly. Once sorting is completed, the child process unmaps the shared memory using unmap file view of the file and closes the shared memory handle with close handles. This ensures that there are no resources leaked. Finally, the child process terminates significantly and signaling the parent that the task is done. So the challenge we coming to the summary, uh, we have discussed about the parents, discussed how the parents.c and the child process.c work together for parallel sorting. The parent generates a dataset, creates a child process, waits for them to complete, and then merges the sorted results. Each child process sorts its assigned portion of data and communicates with the parent using shared memory. By dividing the dataset and sorting in the parallel, we can significantly reduce the time it takes to sort the larger arrays. So the challenge we faced during this approach was is to ensure that that the shared memory is properly managed and cleaned up after use. Additionally, process synchronization must be handled carefully to avoid the issues during the executions. Thank you. The next part of the program will be taken up by my friend Sudarshan.
Thank you, Prajwal. I will be walking you through my implementation of parallel sorting using parent and child process in Windows environment. This is program utilize shared memory and inter-process communication to handle and sort large dataset efficiently. Let's dive into the details. First step on compilation. Before running the program, we first need to compile both the parent.c and child process files to create the executable files. Here is the how it's done. For the parent process, we should write the bash code gcc parent.c hyphen o parent.exe. Let's run the code. This generates the parent.exe file, which will manage the dataset and child process. For the child process, we should write the bash code gcc child process dot c hyphen o child process dot exe. This will take time. Something happened. Let's try once again. Wait a minute. Let's try once again. Now this generates child process dot exe, which is responsible for sorting the array segment passed by the parent. Once the both program are compiled successfully, we are ready to execute. Let's move through the main uh, assignment process page. Now open the terminal. Next, I execute the parent program using parent.exe. Now let's run the program. This initializes the sorting process, and here is the what happens step by step. First, data generation. The parent process generates 10 million random integers. You will see the message generating 10 million random integers. These numbers are the data sets to be sorted. Next, instruction display. The parent process outputs usage instruction like this. Usage mapping name, subject OS and array size 1 million, sorted index 1 million. Here is the 0. Here actually it starts. Next, these instructions show how the child process will sort their respective portion of the array. For example, start index indicates where the subarray starts, and array size specifies how many elements to sort. Mapping name is shared memory used for inter-process communication. Next, sorting and merging. The parent process splits the array into smaller segments and assign them to child process. Sort its assigned segment and writes the result back to shared memory. Once all the child process completed their task, the parent process merge the short subarray into the sorted array. Next, we will discuss about the output. Here the here is the output total sorting time. Now let's go through the output step by step. Here is the output. Here is the sorted. Here is the total time taken to sort the subarrays. This is shows how fast the program performed sorting using parallel processing. 1.1 seconds it will take to sort the subarrays. For the first sorted elements, 10 sorted elements, the parent process displays the first 10 elements of the final sorted arrays for verification. This confirm that sorting was performed successfully. Next, move through the sorted array.txt. Finally, the result are written to sorted array.txt. This file contains two main sections. First one is subarrays. Each child process outputs a sorted segment of the array. For example, this is the subarray 1, first 100 elements. This is subarray 2, first 100 elements. This verification that each child process sorted its assigned segment correctly, and here is the final merge sorted array of, here is the first 100 elements. After merging all the parent process outputs, the first 100 elements of the completely sorted array, this is the completely sorted array. This confirms that the successful success of the overall parallel sorting algorithm. From this, we will know that the parent process splits the dataset into segment and assign them to child process. Each child process sorts its assigned segment in parallel. The parent process merges the sorted segment into single sorted array. This implementation demonstrates the efficiency of parallel processing for large datasets. Now, further conclusion will be continued by Prithvi.
Thank you, Sudarshan. The final conclusion is that the proposed program efficiently sort 10 million integers using parallel processing. Each child process sort its assigned subarray independently, ensuring correctness through process isolation. The merging process implemented using a mean heap guarantees that the final output array is fully sorted with optimal time complexity, and the program leverages parallel processing to significantly reduce sort time compared to single process execution. The use of Windows API function like create process, create file mapping, and map view of file ensures efficient memory usage and fast inter-process communication. This setup eliminates the need for slower file-based IPC methods. And these key observations are parallel sorting reduces the total sorting time when compared to sequential sorting. The merging process is efficient due to its reduced time complexity of O of n log k. Sorting time scales well with increased data size due to the use of multiple child process. Coming to IPC implementation, the choice of shared memory with create file mapping and map view of file ensures direct access to memory across processors, minimizing data transfer overhead. This implementation is faster and more efficient than alternatives like pipes or files. On UNIX based systems, mmap serves the same purpose, providing a cross platform reference. Coming to resource management, proper cleanup is ensured through the use of close handle, releasing all resources associated with processes, shared memory, and file mappings. The program gracefully terminates all child processes after sorting, ensuring stability and preventing memory leaks. And coming to the documentation, the project includes clear, well commented source code. The documentation explains the following in detail: choice of IPC methods and reason for selecting shared memory, and also step involved in the merging algorithm, and observation on performance and efficiency with performance logs. And the final remarks are Strength. Coming to strengths, the program demonstrates an efficient and scalable solution to sorting large data sets using parallel processing and shared memory IPC. It effectively uses Windows API functions while providing a UNIX equivalent reference. Challenge addresses are handling large data sizes, ensuring correct parallel sorting, and optimizing the merging process. The future improvements are consider dynamic load balancing to handle uneven workloads in real world scenarios. Explore additional IPC methods like message queues or named pipes for comparison. Test with larger data sets to evaluate performance scaling further. Overall, this project successfully demonstrates a robust and efficient approach to parallel sorting and merging, showcasing both technical correctness and performance optimization.